Good afternoon. Today I will present a new approach to fair packet scheduling for the internet. This work is a collaboration involving my colleagues and mentors at Johns Hopkins University, Hewlett Packard Labs, and UC Riverside. Packet schedulers are a crucial part of our networks that are shared among millions of active users, connections, and flows. And the job of a packet scheduler is to arbitrate the sharing. What are the characteristics of an ideal packet scheduler for our internet workloads? Offering low latency for latency-critical applications like our Zoom calls. Offering high throughput for large flows, such as file transfers. Fair bandwidth allocation to ensure that everybody gets to use the network without the need for explicit tuning or configuration. We use packet schedulers more than we imagine we do. Our host networking stacks employ a QDisk layer that embodies a software packet scheduler. Packets are then inserted into ring buffers, and our commodity NICs do another round of scheduling among those rings. Packets in the network also face many instances of packet scheduling in switches and routers. And even our I/O and process schedulers implementations in our operating systems use a variant of fair scheduling. There's a strong body of literature on fair queuing and fair scheduling. There's also a large body of work that rely on some sort of fair scheduling in their designs. And interestingly, most of these systems simply use a variant of round robin, such as deficit round robin. A genius method that was introduced in 1996, and its goal was to support workloads with different packet sizes and also to be practical and implementable. A property that was lacking in the classical fair schedulers that were introduced before. One example is the self-clocked fair scheduler, which sorts all the arriving packets based on their arrival times and offers tight bounds on fairness. And this was the basis for many follow-up schedulers, such as the start time fair queuing and deficit round robin. And even the design of the CFS process scheduler is also inspired from self-clocked fair queue. However, its deal breaker issue is its queue operations, which are expensive because of the sorting, which makes it impractical for fast packet processing pipelines. And therefore, we resort to DRR, which is fast, scalable, and is built based on simple assumptions about the traffic. First, DRR assumes that all the flows in the scheduler are backlogged. DRR gets an input from the user called quantum that decides how much each flow is allowed to send at each round. DRR then visits each flow subqueue in round robin and selects multiple packets as long as they don't exceed the quantum on aggregate. The remainder quantum is accounted for that flow as a deficit to be used in the next round. In this example, if a small burst arrives, it has to wait for a long time behind large packets because apparently we chose a quite large quantum for our DRR scheduler. So let's use a small quantum for the same scenario. With a small quantum, small packets can be transmitted on first visit, but flows with larger packets must wait to build up deficit. So it would take 3 spins for the purple and the cyan flows, for example, to be able to send a packet. Now, if the bursty flow arrives, it might actually get very lucky and pass through almost immediately without getting stuck behind large packets. And the scheduler goes on spinning and sending packets in more rounds. So the small quantum helped a bit with responsiveness, but you notice it took longer for the scheduler to complete all the rounds because these operations are compute intensive. Now, what is a good value for the quantum then? The authors suggest a value at least as large as the biggest packet in the network, which brings us to their second assumption, that packet size distributions should not be too skewed. But I'm afraid these assumptions barely hold anymore. We computed the burst length distributions from public packet traces from ISPs, backbones, campus data centers, applications, and others. And our results show that less than 1% of the bursts are longer than 10 packets. The packet sizes are also varied. We have packets as small as 60 bytes and as large as jumbo packets and everything in between. Now, how bad the performance can be in the face of this variability? We performed some tests on a physical topology with 8 single packet request response flows mixed with 72 background flows, all using TCP cubic and sharing the same bottleneck that is serviced by deficit round robin. We tried different quantum values for the scheduler and measured the response times and the CPU consumption. So you can see that with larger quanta, the latency goes up because shorter packets have to wait longer to be serviced by DRR. And CPU utilization comes down because we incur less spinning and less cache pressure. Higher CPU usage usually means more pressure on all parts of the stack and ultimately results in throughput degradation if the system cannot keep up. Another thing to point here is that even if we enable all the optimizations in the scheduler, such as the sparse flow optimization that separates the list of new flows from the old flows, we still face this trade-off. Our results highlight that there is no correct answer in configuring DRR, and the dynamic and bursty nature of today's internet traffic make things worse. But this trade-off in configuration is just an artifact of DRR's operation. On the spectrum for fair scheduling, we have the self-clock schedulers that are parameterless, have strong bounds and offer low latency, but they are not practical for fast networking pipelines. And on the other side, we have DRR, which is simple, scalable, low overhead, but its performance heavily depends on its parameter configuration. We found a way to combine these two paradigms while retaining all their advantages. You notice these are the same 5 characteristics of an ideal packet scheduler for the internet that can be found in the self-clocked round-robin scheduler, or SCRR in short. The intuition behind SCRR is that the self-clocking semantics can help remove the rigid quantum. In SCRR, flows are identified using a classifier, and each have their own subqueues. The flow that has made the most progress defines a global clock for the scheduler, and the job of the scheduler is to help advance all the flows in a fair manner while helping the lagging flows to catch up to the global clock. So if we draw the schematic of our queuing system like this, in the eyes of SCRR, packets will be spread over time based on their arrival times. In this example, flows in the previous round have sent a bunch of packets, and those are represented by these empty boxes in front of the queues. And the third queue has made more progress than the rest, so it becomes the global clock. Now, these numbers that appeared above each packet represent the virtual start time of a packet, a value that is assigned to them by the scheduler. How? When a new packet arrives at a non-empty subqueue, its virtual time is set to the virtual time of the tail packet in the queue plus its size. For example, the virtual time of the tail packet is 22, and assume that the size of the packet is 3 units, so we assign 25 to this incoming packet. If the new packet belongs to an inactive flow, its virtual time will be the scheduler's global clock, which is 19 in this case. Now, the scheduler visits each queue in round robin and allows each flow to send until its virtual time of its head packet exceeds the global clock. Here, the first queue in the example has a chance to send multiple short packets until it exceeds the global clock. The scheduler then moves to the next queue and repeats the process. Here, only one packet from the subqueue is eligible to be dequeued, since the rest have a virtual time that is later than the global clock. We then continue the round-robin process. And here, one packet is always guaranteed to be removed from the queue, regardless of its virtual time. And this would prevent starvation and does not affect our fairness bounds. In the fourth subqueue, again, one packet is eligible to be dequeued. And the same is true for the last subqueue. And when all the subqueues have been serviced, the scheduler moves its global clock forward and starts another round. So this is how the scheduling output looks like at the end of the second round, the third round, and the final round. And looking at the scheduling output, the insight here is that we removed the quantum in round robin by replacing it with self-clocking. In fact, one of the key properties of SCRR is that its transmission granularity dynamically adapts to the maximum length packet in the network. So that was the core of SCRR's design, but we didn't stop there. Internet is jammed with short, bursty, and latency-sensitive flows, and for each of these properties, we made further adjustments to make the scheduler faster and more efficient. For bursty flows, we introduced initial advanced enhancement so that light bursty flows can initially send multiple packets without violating the scheduling bounds. Here in this example, the scheduler sends packets of the same color at each round. Now, suppose that the last subqueue suddenly becomes active at the end of round D, and according to the original self-clocking principles, we assign its head packet the global virtual clock of the scheduler. And with this arrangement, this new flow will require 2 rounds to transmit its packets while competing with other flows. However, theoretically proven, we can instead assign the previous global clock of the scheduler to its head packet, which will instead allow the flow to send its both packets immediately in the next round. We also introduced 2 more enhancements to boost the performance of latency-sensitive flows. The sparse flow optimization that uses 2 separate lists for new flows and backlogged flows in the scheduler, and the no-empty optimization that offers a much simpler and more efficient implementation of the sparse flow optimization, specifically targeting short flows. These enhancements do not require any per-packet metadata and are shown to improve the latency of short bursty flows by 45% for request-response workloads and 15% for streaming workloads in a fully backlogged scheduler. All right, let's go back to our trade-off experiment and plug in SCRR results. First, for the latency, SCRR is a no-brainer. It offers 4 times lower latency than DRR's best configuration, and this improvement can increase to 8 times compared to the worst configuration. SCRR also offers 2.6 times lower CPU utilization compared to DRR's worst case, and just 20% higher than DRR's most conservative configuration. Let's also compare SCRR to other packet scheduling paradigms in a similar request-response experiment. Here, we vary the request sizes from 150 bytes up to 10 kilobytes and plot the CPU versus latency for each request size. FIFO queues create severe head-of-the-line blocking, so the response time is usually pretty bad. We tried AQMs, but they are not much effective in helping latency-sensitive flows. We tried admission control in AIFO, which further lowers the latency at the cost of more CPU utilization. DRR depends on its quantum settings. As we saw previously, low quanta would hurt its efficiency. STFQ, as a representative of classical fair queuing, offers low latency, but it's not scalable under large flow counts. And finally, SCRR offers both low latency and low resource utilization. In comparing the numbers, we observe like 15 times lower latency than Droptail, 50% lower latency than the default Linux queue disk, and 20% lower latency than STFQ. I invite you to read our paper. You'll find more results and analysis on all aspects of scheduling performance. We have a theoretical analysis on SCRR's fairness, showing that it offers identical fairness quotient to DRR. This stems from the fact that at each round, flows cannot be more than 1 packet away from the global clock. We show that the burstiness of each flow under SCRR, that is the number of bytes each flow sends at each round, does not exceed 2 MTUs based on self-clocking principles. And we have many interesting results, such as the fairness and discussions about other approaches, such as programmable packet scheduling that can have unwanted effects, such as underutilization or reordering. SCRR is practical and ready to deploy. We invite network designers, operators, and researchers to plug in SCRR in their existing deployments. And finally, I hope that this study underscores the importance of revisiting the design of existing network systems. We showed that the modern nature of internet traffic with short bursts and diverse packet size distributions violates the assumptions used in the design of widely deployed systems such as DRR. And we proposed a true plug-in replacement for DRR that is parameterless, efficient, and fast. And with that, I'm happy to take your questions. Thank you.